Good morning, students. This is FBA 310-36-2 lecture. This is the first lecture. My name is Dr. A.I. Opara. The topic we are discussing for today is probability distributions. Definition. A probability distribution gives the probability associated with each value of a random variable. Now, there are many random variables you will encounter, but let us start with the simplest one, Bernoulli distribution. The Bernoulli distribution is generated by Bernoulli random variable, which has only two values, success or failure. Success is given the value 1, and failure is given the value 0. And probability of success is P. That means probability of failure is 1 minus P. A practical illustration of a Bernoulli distribution is, let's take the example of a producer of pins using a lathe. The lathe machine is not perfect, so the pins produced can be either good or bad. Now, if it has probability of P of producing a good pin, that means the production of a single pin is a Bernoulli, generates a Bernoulli distribution because it can be either good, the pin can be either good or bad. Let's look at the table involved here, the Bernoulli distribution table. Here, X is 1 or 0, probability of 1, Q, P, probability of 1 is P, probability of 0 is Q. Q is 1 minus P. Now, every random variable, that's all. But every random variable has a mean and a variance. A mean in the sense that the Bernoulli random variable will be occurring like 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1. So what is the average occurrence? That we can find using this formula, sigma xp of x. Now, just a second. I'm in class, yo. I'm in class. Yes, yes. Sorry for that interruption. Somebody was coming to help while I was already in class. So sigma xp of x, see where we did it. 1 times p is p, q by 0 is 0. So when you sum p, sigma x squared p of x, square 1, it is still 1 times p, we have this. So when you sum, that's how you get the variance is sigma x minus expectation of x all squared, which is the same thing as sigma x squared p of x minus expectation of x all squared. That's why we now have that the variance is p in minus p squared. When you factorize it, is p into 1 minus p, which is pq. That's all we can take for the Bernoulli. Let's go to the binomial. The binomial random variable generates the binomial distribution. So the binomial random variable consists of the number of successes in n independent Bernoulli trials. For instance, in the lathe machine producing pins, let's say 5 pins are produced. The number of good pins is binomial because the number of good pins could be 1, 0, could be 1 or 0 or 2 or 3 or 4 or 5. Now, this gives the condition for which a random variable can be binomial. The number of trials is fixed, for instance, 5 trials. Each observation is independent, that is, producing a pin now does not influence the production of the pin later. Each observation requires 1 or 2 outcome success, represents 1 or 2 outcome success or failure. The probability of success is P. So you can see we are taking all this from n independent Bernoulli trials, we have said before. Now, since x can be 0, 1, 2, 3, 4, what is the probability that x is 0, x is 1, x is 2? We find it using the binomial function, which is n combination xp to the power xq to the power n minus x. Now, n combination x can be written as n with x below and a very brief bracket. And the combinatorial here is n factorial multiplied by x factorial multiplied by n minus x factorial. Now, what is a factorial? 4 factorial is the same thing as 4 by 3 by 2 by 1 and so on. But the good thing is we are not going to use this formula to calculate the binomial probabilities under the binomial distribution. We will use the binomial table, which we have reproduced for you here. Let's take, for instance, this problem. X wave BI 7, 0.4 means X is distributed as binomial with number of trials 7 and probability of success in each trial as 0.4. That's the meaning of this, what we can call statistical representation here. Sorry, please. Now, if we are given to solve that problem, what do? Let's first of all take probability that X is less or equal to 3 here. That means X can be 1, it can be 2, it can be 3, it can be 4. No, sorry, it can be 0, 1, 2, or 3. So how can we find it? Using the table. This is what we call cumulative binomial table for n equal to 7. There's another table for n equal to 8, n equal to 5, but this particular table is for n equal to 7. Here, so look at our probability 0.4. When we reach here under 3, look at it. The value here for 0.4 for x3 is 0.710. This is not probability that x equal to 3. It is probability that x is less or equal to 3. That's why we call it cumulative probability. It includes probability that x is 1. It includes probability that x is 0. It includes probability that x is 2 and so on. Look at it here. The probability that x equal to less or equal to 3 is probability that x is 0 or 1 or 2 or 3. So since this has given us the cumulative probability, so to solve the problem, probability that x is less or equal to 3, what we do is just pick this as the answer. The second problem, probability that x equal to 4. Look at 4 here, 0.904. This is not probability that x equal to 4. It is probability that x equal to 0 or 1 or 2 or 3 or 4. So how we can find probability that x is strictly 4 alone is subtract probability for x less equal to 3 from probability for x less equal to 4. See where we did it. Probability that x equal to 4 is equal to probability that x equal to or less than 4 minus probability that x is less or equal to 3. So it is nothing but this quantity minus this. See where we specified it out here. Now the next problem, probability that x is greater than 5. Now, for x to be greater or equal to 5, that means x can be 5 or 6 or 7. Look at the sample space. The sample space of a statistical experiment is the space containing all the possible outcomes of that statistical experiment. And we are required to find probability for 5, 6, or 7. Now, the probability of the entire sample space, 0, 1, 2, 3, 4, 5, 6, 7 is 1. So to find this one that we're looking for, we say probability that x is greater or equal to 5 is equal to 1 minus probability that x is less or equal to 4. So we take away these ones, 1, 2, 3, 4, 5, from 1 because we don't need this. This is what we need. And we get the answer as 0.904. No, 1 minus 0.904. Now, the binomial distribution also has a mean and variance. The mean of a binomial distribution is, which we call expectation of x, is NP. Multiply the number of trials times the probability in each trial. Variance is NPQ. Don't worry how we have got about all these formula. Take it, then it can be proved, but the proof is beyond their level. Now, for instance, if you are given y is binomial 15, 0.3, the expectation of x is 15 times 3, which is 4.5. Variance of x, which is NPQ, equal to 15 times 3 times 1 minus 0.3. Then the answer is 3.5. Now, we have another distribution, the Poisson distribution. The Poisson distribution represents the distribution generated by the Poisson random variable. What is the Poisson random variable? The Poisson random variable represents the number of occurrence of a phenomenon per unit time or space. For instance, how many people visit a hospital in a day? How many sick people visit a hospital in a day? It can be 0, it can be 1, it can be 1,000, it can be 2,000. So mathematics gives all the chance that as many as possible, 1 billion, 1 million can visit the hospital, although that may not be possible. So you see that Poisson random variable goes from 0, 1 up to infinity. This is the sign for infinity. That number you will never reach, no matter how you try, you will never reach it. Now, the formula for Poisson distribution is exponential minus lambda to power x over x factorial. Lambda is the mean of the Poisson. Now, again, we will never use this formula. When we say x is distributed as Poisson lambda, we are now saying lambda is that parameter. Lambda can be a number. For instance, we say here, x is distributed as Poisson 2.5. Fine, that is, what does lambda mean? What is the mean of the Poisson mean? The mean of the Poisson means the average value of this particular Poisson random variable over a long time. The average occurrence over a long time. You know, when you keep records, you can find average occurrence over a long time. So that is the mean of the Poisson. Now, how can we find x is less or equal to 3, although the mean occurrence is 0.5? How can we find the probability that in this Poisson, x is occurred twice? That in fact, although the mean occurrence is 2.5, that x occurrence will be greater than 5. All sorts of values. This one, that x will be equal to or greater than 3, but strictly less than 8. How do we find all these probabilities? Let's go to the next page. This is the Poisson table, produced also for your convenience. It's also a cumulative Poisson table. See, the mean of the Poisson process is all along here. 2.1, 2.2, 2.3, and so on. The mean of our own process is 2.5. So this is where we are concerned with. When you go here under 3, this is the probability that x is less or equal to 3. So that's the answer. Look at it here. Look at it here, that's the answer. For x strictly equal to 2, it is the probability that x is less or equal to 2, this is it here, minus the probability that x is less or equal to 1. We have done something like that in the binomial. So when you subtract the probability for less or equal to 1, for probability less or equal to 2, you find probability that x is strictly equal to 2. and that is this minus this. If you go to the table, see 0.544 minus 0.287. So what you get is your answer. What of probability that x is greater than 5? Look at the sample space as well. The sample space, no, sorry, not the sample space. For as we saw in the binomial, probability that x is greater than 5 means x cannot be 5. X can be 6 or 7 or 8 or 9 or 10 to infinity. Excuse me, to infinity. So if you subtract the probability that x is less or equal to 5 from 1, because x cannot be 0 or x cannot be 2 or 3 or 4 up to 5, but x can be 6, 7, 8, 9. So when we subtract probability x less or equal to 5 from 1, we get the answer for what we are looking for this probability, which is this value. Now, probability that x is greater or equal to 3, but strictly less than 8. This means x can be 3, it can be 4, it can be 5, it can be 6, it can be 7, it cannot be 8. See, it is illustrated in this sample space here, where we have mapped out using this circle 3, 4, 5, 6, 7. How do you find probability that this happens within the sample space? It's easy. The probability for x less or equal to 7 gives everything from 7 to 0. So the probability for under 2 gives you 2 to 0. So if you subtract probability for x less or equal to 2 from probability that x is less or equal to 7, then you get the required probability for this region. See where we solved it. Probability that x is less or equal to this, just a minute, see it here, is equal to probability that x is less or equal to 7 minus probability that x is less or equal to 2, which will give you the answer. Now, and we finished it up here. Mean and the Poisson of the Poisson random variable. The Poisson random variable is the only random variable. Well, the only common random variable where the mean and variance are the same. If y is distributed as Poisson lambda, the mean of Poisson is lambda and the variance is lambda. It's unique with Poisson. So for instance, if x is distributed with Poisson 5, expect mean of x is 5, variance of x is 5. That is it. Take it from us. Now, Poisson approximation to the binomial. Let me pose the problem first. Now, suppose I give you this binomial distribution. X is binomial 400, 0.01. Find this probability. Look at it here. You can't find binomial with n equal to 400 on the table. Neither can you start calculating all this with your calculator. What we do say is that if P is small, look at it. If P is small and n is large, such that NP is less or equal to 5 or thereabout, then this x that was originally distributed as binomial cannot be distributed as Poisson with parameter NP. NP is the mean of the binomial. Sorry, that's the mean of the binomial, n times p. So to find probability that x is less or equal to 2, transform the binomial, first of all, to Poisson. Now, to find NP, 400 times 0.01 is equal to 4. So this binomial has changed to Poisson 4. So you can use Poisson 4 to find this from the tables. Now we come to the normal distribution. The normal distribution is a continuous distribution associated with the normal random variable. What do we mean by a normal distribution? By a continuous distribution. Continuous distribution, well associated with a continuous random variable, that is the normal random variable, is such that this random variable can take any value, whether whole number or fractions, within minus infinity to plus infinity. That's a very big range. Just a minute. Minus infinity to plus infinity. Now, the former distributions we've done, binomial, Poisson, they are called discrete random variables. They can only take values of whole numbers. You can't have 1 and 2 third people visiting a hospital. It has to be either 1 or 2 or 3. But a binomial random variable can take fractions, decimal fractions of any type. So a normal distribution is very important because this course, everything you are going to do from now on will involve one aspect of normal distribution or the other. Let us look at them. So please try to understand it. Let us look at the characteristics or properties of the normal distribution. It is a bell-shaped curve, and it has both a mean and the variance, and the mean and variance are called parameters. See how it is shaped, the normal distribution. Now, look at this curve here. The mean is at 10, it's at the center of distribution, 10. Now, that's the mean. What do we know about the variance? Look at, from here to here gives us one standard deviation, which is this 10 has added 2. If the standard deviation is 2, therefore the variance is 4. From here to here is another standard deviation away from the mean. So if here is 10, here is 12, this is 14. On this side, the value of the random variable is decreasing by the standard deviation. Here, it is now 10 minus 2, which is 8, 8 minus 2, which is 6, and so on. So you can see how the variance, and by implication, the standard deviation, helps to tell us much about the normal random variable. So what we are saying, the normal distribution is symmetric about the mean. In fact, you've seen it here already. What happens on the positive side of the mean increase, the rate of increase. That same rate of decrease occurs on the left of the mean. We say that it is symmetric. It is not normal distribution is not the only symmetric curve, but that's the one you meet for now. Now, one thing about the normal distribution, see, within this area, that is minus 1 standard deviation to plus 1 standard deviation, lies 68% of the values of the normal random variable. Now, within 2 standard deviations away from the mean, that is 2 standard deviations away from the mean on the left and 2 standard deviation on mean on the right, lies 95% of the values of the normal random variables, which we say mu minus 2 sigma. Sigma is a standard deviation. Mu plus 2 sigma. Sigma is a standard deviation. So within this interval lies 95% of the normal random variable. It is a beautiful story in that if you know the mean of the normal distribution and you know the variance and by implication the standard deviation, then you know that within 1 standard deviation to the left or right, you have 68% of the values of the random variable. Then 95% within 2 standard deviations left or right. And of course, 99.7%, almost all of them within 3 standard deviations to the left or right. So it is easy to almost exhaust the whole values of the normal random variable, but by the time you come to 3 standard deviations away from either the left or the right of the mean. I hope you appreciate this. Now, How do you find probabilities under the normal distribution? Again, the function which defines the normal distribution is 1 over square root of 2 pi sigma squared multiplied by exponential. Exponent is a function which you must have heard about it, to the power minus half into x minus b all squared. Again, you will never use this function. There are tables you can use. For instance, if we are given that a random variable is normally distributed, it will be stated like this: mu is the mean, sigma squared is the variance. We do not state the value of a normal random variable in terms of the standard deviation. It is always in terms of the variance. Even if you are given standard deviation, you convert it to variance. For instance, you can be told that x is normally distributed with mean 100 and variance 64. That is x. Now, given that this, let us see how do you find probabilities under the normal distribution? For instance, first of all, look at what probability means under the normal distribution. This normal distribution has mean 60. And this value here, 51, you see the shaded part here. The shaded part represents probability that x is less or equal to 51. Probability under the normal curve is an area. This is one property enjoyed by continuous distributions. Probability under the normal curve is an area. You will not start calculating these areas. They have been calculated for you, given you in a table. Look at here. This is the mean of the same normal distribution. This shaded part represents probability that x is greater than 69. Probability that x is greater than 69. Look at this shaded area here. It gives us the probability that x lies between 51 and 69. In the normal distribution, you can't find probability that a normal random variable is a specific figure, like probability that x equal to 40. No, is 0. There's nothing like that. Probability that x equal to 70 is 0. For any normal random variable, probability that x is a fixed quantity is 0. It's always probability that x lies in an interval. Here, the interval is below 51 to minus infinity. Here, x lies from 69 to plus infinity. Here, x is constrained within 51 to 69. We've just explained what probability under the normal distribution looks like now. But there is a special normal distribution, the standard normal distribution. The standard normal distribution has mean 0 and variance 1. That means standard deviation is also 1 because square root of 1 is 1. Look at the picture of a standard normal distribution. See, the mean is 0, 1 standard deviation to the left, 1 standard deviation to the right, 2 to the left, 2 to the right, and so on. This is a true picture of a standard normal distribution. If we want to find probability that x is less than a certain quantity, look at it. Here is A. It is still the shaded part. Now, let us now do a real problem. X is normal 0, 1. Find probability that x is less or equal to 1.5. Probability that x is less than minus 0.56. Probability that x is greater than that, and so on. First of all, now, sorry, just a second. If you have the normal tables, please bring them out, standard normal tables. Bring it out. I'm giving you 1-2 minutes, a minute to do that. Open the page where you have standard normal distribution. If you read the standard normal distribution, open the page, go to the first column is called Z, the Z column. Continue going along that Z value until you see 1.5. When you see that point 1.5, read 1.5 under 0, because 1.5, there is no more value here. That's why it is under 0. See, there's no value here. So it's 1.5 under 0. The value is 0.9332. Again, let us find probability that Z is less than minus 0.56. Go along that Z column until you find minus, what you find is minus 0.5. Hello? The class has been on since, so I was talking to myself. Okay.